Hello, hello, hello. Welcome to the show. My goal today, right now, is to, what is it? Exit that. I want to go and look at the kernel again and show you some more stuff. And then we'll get straight into some other funky findings, okay? I hope you can see this. This is the boot file here, okay? This is the whole Linux operating system. You have a kernel here, your init here, include files, memory management, okay, your tools, your make file, and everything else like that. This here, in the GC. This is actually what Linus wrote down. This is his actual file. You know, so make file for Linux if you don't have mstring blah 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 in your GCC. Okay, this is. I want to say. Actually, I'm not going to kid you. I don't know what the hell this is. Okay. Alright, but it refers to the kernel. Now you see, this is a make file for your kernel, I guess, to make and compile the operating system. Yeah, makes sense. Okay. But what exactly is it? I don't know. I don't know. I don't know. So that's that. That's one thing. Look at date. It's pretty cool, isn't it? 1991, September 17th, 91, right? That is pretty cool. Here's your kernel. Okay, these do not contain assembler on a most grandiose scale. Okay, most of this is C. Okay, this is all mostly C. So, but C can access, can implement assembly language. Okay, now this is the file system. Holy crap. Interrupts, IO control. Okay, like look at this. This is just crazy. This is the C program. This is your kernel. This is the first kernel. Right? Yours is a derivative from this, and there's some improvements and whatnot like that, but this is actually pretty daggone interesting. Include files. Okay, and .h is, we got signal. Let me get something here. Standard definition. Standard defines maybe. Okay, so this is all C program. All right, this is our operating system, our firstborn operating system. Here's assembly code, or it says .asm. All right, I have no idea what that stuff means. What is it? That might be inline assembler. Stuff like this. You see underscore sem underscore. That looks like assembler. I'm not sure, but that's inline assembler. That's a different. It's a GNU assembler. It's an inline assembler. All right. It's a different type of assembler. All right. And I'll get back to the different type of assembler in a second. Alright, this contains 32-bit startup code. Okay, this is what gets loaded. Let's see here, reload after, or reload all the segment registers here. Look at that. Alright, hope you can see that. I can't zoom in, but I hope you can see that. What it's actually saying, move, blah blah blah, percent EAX. Now, I want to talk about that percent, and I'll talk about that in a second too. Oh boy, I can't talk about two things at the. I forgot what I was going to talk about before this, but no, the GNU assembler. I want to talk about this percent EAX. Okay, you see here, move, percent AX, and percent DS. Okay, data segment. Okay, DS is data segment. Move the contents of AX into extended segment. Okay, stuff like that. Now this looks a little different. Uh-oh, I just changed that backwards. Get out of that. No, I don't want to save this. I want to talk about that. That's syntax. Okay, if you see here, this is syntax as well, but this does not have any percent signs or anything in here. Okay, so first I'm going to talk about GNU assemblers, inline assembly first, and then I'll talk about what the syntax is and why there's a different type of syntax. Okay, and I can do all this in less than 5 minutes. Okay, there's some more code down there. Alright, so basically, basically, we will say CD in a desktop, DOS. Let's vim tiny something. Okay, .txt. Basically, assembler. What does assembler do? What is assembler? Okay, assembler. Assembly language. Deals with the direct movement of the processors, like I said before. Okay, direct movement of things in registers and boxes in the processor. Okay, an assembler is a somewhat interpreter. Okay, it's an interpreter that uses special syntax. Uses special syntax, okay, to move, to do exactly the same thing, okay? So instead of typing in move and all this stuff like that, jump not equal, compare, and all that stuff like that, it still uses those, okay? But it does it in a different way, alright? And Torvalds used the GNU inline assembler to write some of his assembly code. Okay, especially in the C in some of the C files. Okay, in some of the C files he used GNU's inline assembler. Okay, I don't know how to do that. Okay. There's also other type of assemblers, like I talked about in the first tutorial, which is a NASM assembler, which is a net-wide assembler. Okay, TASM, I don't know. There's a YASM. All right. I think that stands for yet another assembler. You could write your own assembler. Okay. NASM, TASM, FASM, which is a flat assembler. Okay. MASM is a Mac assembler. WASM, I don't know if that exists or not, but if that's the case, then it's a Windows assembler. Right? Okay. Or any other assembler that you want. And the difference between these things known as assemblers is, let's say Nautilus here. Let's go look into the source. S. Oh my God, SS. Where are you? S is sources. If we look at the source code here, back to the Linux operating system 0.01. Okay. If we look at this, all right, all this is comments and everything else like that. See this area here? Entry start with a colon, okay, go. These are defined variables and functions and stuff like that, okay? Do move is a function that he decided that's what he wanted it to do. End move is another area or a function that he wrote and decided to do, okay? See here, he's talking about protected mode and everything else. I mean, this is just great. Okay, These are all, say, defined functions, okay, that include assembly code, okay, to do certain things, okay. Now, you can't just go ahead and type in OK to read, all right, inside of your computer at such a deep level and expect it to do anything. It's not going to do anything. But you can type in move AX. That's a bad example, but you can say add the contents of add into AX register this memory address. You can say that directly to the computer through assembler, okay. But what this is, whatever assembler he used, and it was the GNU. I don't know if it was GNU inline assembler or not, but this is the type of program that Stallman wrote so that he could add these in, and so that he could have functions and he could have variables and stuff like that. Okay, so that's that. It is a quote interpreter. Okay, it is an interpreter that he used so he could create functions of his assembly code. Okay, all this stuff here, as long as it's not calling any functions, will work. Okay, but you don't want to have to call these things every single time. Okay, made it easier with declaring variables, and that's that. Okay, so that is assembly. That is when you use an assembler. Okay, and assembly code is stuff like I said: move, jump not equal, jump not zero. Alright, we'll go over that syntax in a minute. Okay, but that's what that is. And there are many interpreters, like I said. A very popular one, especially for Linux, is NASM. Okay, it's a net-wide assembler. And the good things about NASM is that you can actually write code. You can write code for 32-bit, okay, Windows and Linux machines at the same time. Okay, you just have to change a couple variables at the very bottom, and you can probably do this on many other type of interpreters too, or assemblers. Okay. Okay, that's that. What I am going to do is I'm going to use DOS. Okay. Now, DOS uses its own assembler, does it? I don't want to say that, but I do know one thing. DOS is Windows. Yes, it is. DOS is Windows. But you're moving stuff on the processor. Okay? And I have not had enough time to figure out NASM. So I'm starting with the basic of the basic. Okay? Which is DOS. And when you write stuff, you write data segments, you write them directly to the hard drive. It does not go through anything else, like a net-wide assembler. It does not go to a net-wide assembler or anything. Okay? And I'll be emulating that to a DOS box and a DOS EMU on my Linux machine. Alright? But the reason why I want to use DOS is it's a little easier for me because NASM doesn't have the greatest documentation. Okay, neither does the GNU assembler. Doesn't really inline assembler does not have the greatest documentation that I can understand and pick up on. Neither does AS, which is the GNU assembler. It does not have the greatest stuff. But like I said before in the first tutorial, DOS was everywhere, and there's a lot of leftover good residual data about it. So if I can figure out how to move stuff from one part of the processor by using DOS, and then switch that over to where I can think a little bit on my own, and then use a interpreter where I can maneuver on my feet and know exactly what's going on, not be overwhelmed by this and that. That's what I'm going to do. Okay? So that's that. We'll get into DOS syntax, which is it's really no different than any other assembly syntax at all. Okay, the only thing that's different is something called interrupts. Okay, but first I want to talk about the syntax of list. I want to go back to our C program that we wrote, or I wrote, okay? And I want to say, I want to use object dump. Object, okay, dump. This dumps the assembly code, okay? It takes switches. The switches are D for disassemble, alright? Let's put them out at an H, okay? Alright, this is all the, whoa. Let's type it out, help. Type it out, man, object, dumped. Okay, you can look through this manual all you want, okay? There's a lot of great stuff in here, alright? But I'm not. So, let me exit this. And I'm going to object dump like we did in the last one so we could see the assembler code and see actually how the machine is functioning. I'm going to object dump. Object dump, by the way, only works on executable files. Okay. I'm going to use the D switch for disassemble. Okay. Then I'm going to use the M switch for machine architecture. Okay. And I'll show you in a second. And I'm going to say Intel for my machine architecture. And I'm going to dump a dot out. Okay, we've seen this in the last tutorial. Alright, we noticed the push, compare, jump, equal, all that stuff like that. But what I want to talk about, how come I can't zoom? Dear God. Control 0, control small, control plus plus. Alright, yes, come on, don't show me anything. Yes, 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 okay. What I want to talk about is the syntax, okay? Right now, in the object dump, I typed in, I wanted to specify it machine specific for Intel syntax. Alright, there's two popular types of syntax. Intel syntax, and there is AT&T syntax, okay? AT&T created Unix, okay? And so, of course, they're that's why they're here, right? But the way that Intel syntax goes, and I like reading it in that better, alright? The way the Intel syntax goes is you would say first, here is an instruction to add the contents of or the instruction is add into the ESB, or extended stack pointer. If you go to somewhere else. Add. Jesus God. Here's another one. Add. Add. The instruction is add. Add into the EBX register. We already talked about that. Alright. This memory address. Okay? So basically that's exactly what it's saying. It's saying to add into this register this address. That's how we read it, okay? With Intel syntax. Let's go to another one. We'll say move, no ops, move, no, test, move. Okay. Here's another one. You're going to say move is the command or instruction. What are you going to move? You're going to move into the EAX register. What are you going to move into it? You're going to move this address into the EAX register. Okay? Here's a test function. Okay? Test what's in EAX with what's in EAX. Or move this, or it's just testing, side-by-side testing. Okay? Here's another one. Move into the EAX register. What are you going to move into it? You're going to move the data segment at this address into this register. Okay? That's stuff like that. And it's not that complicated. It's not that complicated. You have to get in the swing of knowing what you're looking at, and knowing syntax and what exactly it's saying to do. Okay? This is with Intel syntax. I like to use Intel syntax better than AT&T syntax. And I'll show you why. let's do another one. Let's say subtract. Subtract. I don't want to do subtract because extended stack pointer, that deals with something else. But here, okay, remember we talked about the stack before, right? Say if the stack is a stack of blocks, that's a good analogy. A big stack of blocks, okay? You want to take off or pop off blocks. Pop what blocks? The contents that were on the stack. I'll get to that later. Alright? Compare what's already in this EAX register with this address here. Okay? So you can actually think about this as moving this into that register, or comparing this back into that register. Okay? So that's the forward type of reading, or this is Intel syntax. All right. Now let's cancel this, clear this up, and we will say something like this. We will say, instead of, we're going to disassemble the same file, okay? But let's use, remember the M switch is for machine type. Let's use AT&T syntax for this particular our scene file we just looked at. Okay, now this is different. All right. This looks different, and from what I understand and what I kind of know too, it's a little harder to read. All right, got all these percent signs here, kind of screw you up. Okay, but this is a straightforward approach. All right, this is a straightforward approach. Let's find a move command here. Okay, we're going to say move this bit of data. No, let's not say that. Let's say add. Okay, we're going to add, what are we going to add? We're going to add this memory location, okay, into the EBX register. Alright, and it might be a little simpler even to do it like that. I am not accustomed to this, okay, but it does go straightforward approach. Compared to the Intel syntax, we had to say add, add, and what we wanted to add was after the location. Okay, with this, you're just saying add this memory address right into here. Okay, so it could be simpler. It could be simpler. And it could be made simpler. Alright? So that's that. The same thing here. We're going to test. Well, test is a bad thing to talk about. Subtract. Subtract this memory location from extended stack pointer. I'll talk about it in a second. Or move this memory location into the AX register. Okay? But I've seen some instances where it kind of breaks down and really gets a little confusing, and I don't need that much confusion when I'm trying to learn something. Okay, so I choose Intel syntax over AT&T stacks. Okay. What is this stuff over here? It's not that important, but it's definitely hexadecimal. Okay. Look at this over here. These are memory address locations. See that? See that? Alright, well, what we're going to get into, it does not look this complicated. These are our address memory locations. Okay? See, 4C skips up to 4D. Okay? Why doesn't it go to 4E? Because there's 2 bytes of information here that take up 2 different locations. And then it skips to 4 or 6F. Okay? You got 70. Okay? 70 has 3 bytes of information. 1, 2, and 3. Then your next, moving down the line, if you can imagine the way that we read a list, a shopping list, similar to the way that a computer reads, okay? And that's where I want to talk about, I'll elaborate on it more later, but it's something called a stack and a pointer. if you imagine this whole column here to the left, imagine this whole column to the left, okay? Move it off screen so you can get a better idea. Imagine this whole column over here to the left as being stacked on top of each other, or a list, okay? The machine will read from top to bottom. It'll read the next address, next address, next address. That's all it does, okay? Now, certain things get put in certain areas at certain times, okay? What reads this, we can say to be a pointer or instruction pointer, okay? An instruction pointer says, okay, this is the instruction I'm on now. Next is this here, okay? And there's base pointers and everything else like that. But that's basically what's going on here. Like, look at this here. What the hell? Like this, I don't know what this means. I have no idea what this means because I'm not familiar with AT&T syntax so much. I do know it says move, yes, move, and AT&T syntax says move the location. I don't know what that means. I can't translate that for you, okay? And it's no biggie that I do, okay? So that's the difference between syntax, types of syntax, and there are many types of syntax, but the most commonly used ones are those two, okay? And then again, where am I at? Okay, then again, let's go back to our kernel, our Linux 0.01. Let's go back here and look at exactly what I was talking about before. What is this? Okay, and the boot file, the boot.s file. Okay, let's look in here. Right here, ignoring that he's using any type of assembler or anything else like that, or any type of interpreter or anything, if we look at this, we can definitely pick up on the syntax right away. Okay, look at the syntax. This is Intel syntax. There are no percent signs, nothing like that. There's a pound sign, right? There's no percent signs signifying special registers. That's the only difference between Intel syntax and AT&T syntax, okay? You're going to say move. You're going to, let's say, move AX into the CX register. That's how Intel rolls, okay? We're going to add BX into our CX register, okay? Might seem a little crazy to skip from one point all the way over to the other side, but after you get used to it for a while, it's not that bad, okay? And it's kind of nice and laid out there, a little neater than with in AT&T syntax, okay? Now he did use AT&T syntax here. I think it was here. Yes, he did, okay? And this over here, okay? You can see here, move AX register and data segment, or DS register, data store maybe, I don't know what that is, or GS, move, let me find something else, a nice little move instruction. We see how complicated this starts to look after a while, alright? I can't go that deep right now, I don't know that much. Move, I don't know what the W is, but if we just said move, we could say move move the DX register, or what's in the DX register, into the AX register. Okay? Move the contents of DX into AX. Okay? So those are two types of syntax. Jump greater than, stuff like that. He used two different types of syntax, and it's no problem because it's all at a machine level. Okay? And obviously it worked out. Obviously it worked out great for him, because if not, we would not be using what we're using now. Okay? So that's all I want to talk about today. That's all I want to talk about today. And we'll get to looking exactly at this. Get this. Alright? I hope you can't hear that grinding noise or anything. But get this. Get this. Get DOSBox. Okay? Get DOSBox. We're going to be using it. Okay? And you can do that by going and saying sudo apt get install DOSBox, right? And do the proper installation to it. Okay. Another thing I would say to you to get is DOS-EMU. For some reason, my DOS-EMU only runs as root. I don't understand that. All right. 5.3. DOS-EMU. Okay. Debug dump. Say Redis. Okay, yeah, great. This is definitely something I'm going to talk about later. And if you want to pause this real quick and take a look at this, this is exactly what we're looking at. I don't want to get into it, but this is exactly what we're getting into. AX, BX, these are contents of your registers. You can see AX is zeroed out. There's nothing in it. CX register, DX register, stack pointer, base pointer, all that stuff. All this stuff is familiar to us. It's all data segments that came out. It's the same thing, trying to interpret what's going on in this hexadecimal format. Okay, these are code segments here, code segment addresses, and to be more specific about this side over here, this is a data segment. Okay, this is where the data segment is, and you notice that it jumps over to 110. This is a data segment. This is a code segment. All right, we'll get into that. Pause it. Take a screenshot if you got it. Ready? 3, 2, 1. I'm leaving. Okay. So that's what it's going to look like. Get DOSBox. Get DOS-EMU if you want to. Okay. Get FreeDOS. Okay. FreeDOS uses a Linux kernel. Okay, is a FreeDOS, because if you don't have DOS, I downloaded mine. DOS. I downloaded DOS 7.1, 7.0, I think, something like that, and I burned it and I put it on a machine, right? Because I had problems with FreeDOS. FreeDOS gave me some problems, and I was having too many problems. Okay, and so I first did the DOSBox, okay, and the DOS emulator. Okay, they were giving me problems at first, so I just burnt one and put it on another hard drive on an old computer I got, and I ran DOS from that. Alright, so you can do that, or if you don't have a whole bunch of computers laying around like I do, just go ahead and type in DOSBox. I think DOSBox may be, oh shit, DOSBox may be required. DOSBox may be required, okay, to run the DOS-EMU, right, or DOS emulator. Now the reason why I'm running two different DOSes at the same time is that DOSBox, the program DOSBox, doesn't have the debug feature into it. Okay, so DOSBox is good for old games, right? Old 16-bit games, right? Like Mario Brothers and stuff like that. You know what I mean? A lot of people use it for that, or play Mario on their phone, or play Mario on their computer, and they're like, "Oh wow, this is cool." Yeah. All right, it is cool, but the only thing you're doing is playing a game. What else are you doing with it? You know what I'm saying? So DOSBox is not only good for providing a virtual space for games, but is also good for running a virtual DOS operating system. Okay, but DOSBox does not come with debug. Okay, and debug is the platform I'm going to be using to explain more about assembly and more about machine code. Okay, so I have to run debug, but DOS doesn't come with debug. However, DOS-EMU, that program, the program DOS-EMU does come with debug. Okay, and there is a debugger for Linux. I don't know how to use that very well, and there's not too much help about it. Okay, but DOS-EMU does come with debug. So, but I don't think DOS EMU runs alone by itself. I think DOS EMU has to have DOSBox running too. Okay, so that's all I'm doing. Alright, for this purpose on this. Or you can download DOS if you have DOS, get it, put it on something if you want to. If not, whatever. You can maybe even put it in a virtual machine. I tried to put it in a virtual machine at one time, but that virtual machines and I seem to have problems, and I don't understand why. Okay. Free DOS, like I said, you can go ahead and you put it in there and blah blah blah. DOS is kind of general. You can even run this if you have a Windows machine. If you have a Windows machine. If you're a Windows user. I hope you're not. But you know what? I hope you are. I hope you are. Hope you are a Windows user. And I hope that you're fed up and you're coming over to the other side to look around and say, you know what? I actually want to learn something with what I'm doing here on the computer. And maybe I should switch to Linux. Yes, you should. Okay? But if you're using a Windows machine, you can go into your command prompt, okay, and you can type in debug, alright, and you will get DOS, okay. You'll be able to use DOS from there. You'll be able to move stuff around in assembly from your Windows command terminal, okay. Okay, so that's that. Get the stuff. Use your judgment on how you're going to get the stuff, okay, and I'll catch you guys in the next one. Word to the bird, man. Hope you guys are having a lot of fun. I've been trying to keep these a little shorter, but it's not working at all. Kill 35, 39, 55. Peace out.